People, that's not crawling all over your wall. People, it's too.
So welcome everyone. I can see that people have started joining. So this is
I'm not sure I understand.
Our webinar on some next generation geospatial trends on cloud native geospatial data formats, and we'll start the presentation in a few minutes. Just give some time for a few more attendees to trickle in. So yes, again, welcome. We're wait another minute for people to trickle in before we start. All right. So let's start. So welcome again. So we're going to today we're going to talk about some of the new things that we see happening in geospatial here in early 2024, and we're going to focus on some of the trends around cloud native geospatial formats. So there's a number of things coming together in the geospatial world right now, and they're tied together by this topic. And so we're going to talk a little bit about what this vision is the cloud native geospatial future, and what do we even mean with cloud native in this context. We're going to discuss some of the exciting new cloud native geospatial formats that are being developed and standardized. Now, even as we speak, there's the new open table formats that build on top of these. Some very exciting, massive new open geospatial data coming online that's interoperable, and also new open tooling. And we're going to think a little bit about what kind of opportunities this gives for geospatial tool makers, including Foursquare, of course. And we're going to end up with some use cases and demos. And we'd love for this to be interactive, and we're hoping to have a Q&A session at the end, and love to hear the audience's thoughts on the topic. So I'm Ib Green. I'm a distinguished engineer here at Foursquare. I've spent last decade pursuing my passion for geospatial things. both building open source projects in for visualization and loading of parsing of geospatial data and analytics and so on. I'm going to touch a little bit about those at the end. And I'm joined by my colleague Aditya Bumbla, who's a geospatial engineer here at Foursquare, and he's going to help me do the demo at the end. So this obviously the geospatial, anyone here is, I assume, a geospatial practitioner or aware of, things in the geospatial world, and we've always had a new, the geospatial world has always, enjoyed producing new data formats, and so, the new data formats that are coming up now, what is different at this time? And there is a vision holding together a number of these initiatives, and it's being articulated now by a number of different key players in this community as the cloud native geospatial vision. And the basic question is, what would the geospatial world look like if we had built everything from the ground up on the cloud? And I'm just going to make a note here that when we talk about cloud and cloud native in this talk, we really mean cloud storage. Cloud native has been a term for a number of years that really refer to a software development lifecycle revolution where we talk about containerizing, our services and using open container formats and maybe virtualizing them, orchestrating them with Kubernetes and so on. And that's not what this is about, although these formats and solutions likely would work incredibly well in that kind of environment. So why is there a need to create a set of new cloud native formats? And notice that I don't even say geospatial here. So cloud native data formats is bigger than geospatial. And so it's cloud storage that has emerged as the big game changer. So it has these incredible advantages. The cost of cloud storage is notoriously cheap. It's incredibly scalable. It can handle even up to petabyte scale data with very little effort, other than obviously paying increasingly large cloud bills. It's extremely reliable, and there's the simplicity of being able to serve to the internet directly from your storage. And so these are obviously things that we would love to take advantage of for geospatial data. Geospatial data is typically extremely big. And so, but there are limitations. So the cloud storage, the object storage model is really optimized for fewer, larger files. And it's typically a read-only model. So you don't really modify one of these big files when you put it up there, but you can read, many times from it and concurrently and efficiently. And of course, there are other limitations like, latency and so on that also play in. And so cloud native formats is really about capitalizing on the advantages of cloud storage while overcoming the limitations. And so these formats are quite different, but there is a theme, which is that they favor very large files, often single files for even a very, very large data set. But these files then have an internal organization in small addressable chunks. And so because they are big files that contain all the data that you need and that you then are supposed to read from many times, they're perfect for hosting as flat files on S3, Google Cloud Storage, and so on. And the chunking is very important because there is typically an index chunk, sometimes a little bit more complicated than that. But once you've read this index chunk, very small part of the big file, the client knows the start and end of all the chunks in this really, really big or massive file. And now we can use what's called HTTP range requests to do partial data reads against cloud storage and only read those chunks that we need, which means that even a browser, for instance, that has limited amounts of memory internally and may have a limited bandwidth for its connection can work interactively with massive data files in cloud native formats. And so we've been working on this for a while. We've been implementing these formats here at Foursquare. We've even been involved in the standardization, for instance, for the geoparquet format. And so we've been excited about that. But as we look out in the bigger community, we see that there is an uptake across a number of different areas that really bring these technologies together. And so the 4 pillars in our way of thinking about this is the formats themselves, and we're going to talk a little bit about what they are and their characteristics. And they are very flexible, and you can do a lot of things with those directly. But on top of those, independently of the geospatial aspect, there is another emerging set of technologies which we call open table formats. And these allow you to take cloud native data in cloud native file formats and turn them into full-fledged databases with not only read, but you also have write functionality, and you have update functionality, and you have transactional integrity and so on. And in parallel with this, a number of really impressive, massive open data sets are emerging, and they are also being published in cloud native formats, giving access to types of data that we really didn't have, easily accessible in a free and open way in the past. And in parallel with this, the 4th pillar is that tooling. There's some existing tooling and some new, really amazing and exciting tooling that is really embracing these cloud native techniques. So there is actually a foundation, the Cloud Native Geospatial Foundation, which is a non-profit foundation that is dedicated to driving the development and the adoption of these technologies. And they have a longer list, so it's a growing list of geospatial formats. As usual, there is no solution that fits all problems, and so slightly different formats are often useful in different cases. But the ones that were particularly maybe at the top of our list are a couple of formats. We have GeoArrow, geoparquet, flat geobuf, PM tiles, cloud optimized geotiff. There's also GeoSAR, for multidimensional data, and COPSI for hierarchical point clouds and so on, but they're a little bit outside of our current focus. And then there is a kind of parallel format that's called STAC, the Spatial Temporal Asset Catalog, that can tie all of these together and help you find and index resources in these various formats. So maybe the granddaddy of all of these formats would be Parquet and geoparquet. And so Parquet has been around for quite a while, and it's been used in these types of cloud native techniques already in tools like Hive and so on. And it's a binary columnar format, so it's a very, very efficient way. That's the most efficient ways of storing tables and then loading them in very efficiently into binary format in the computer. But it's also on top of that optimized for on-disk storage. So it has encodings and compressions that really allows it to do a very high level of internal compression. It also has a rich type system. Binary data needs to be typed, and it also has a certain limited ability to stream or read parts of the file. It's split into row groups that are independent chunks, and within those, the various columns are independent chunks. And we've been working with geoparquet, which is recently released, and it adds It doesn't change the format, but it adds some conventions around the metadata so that one can now portably describe geo columns in geoparquet, and also defines the encoding. And obviously other things in the metadata, like the coordinate reference system and so on, can be described. And there's ongoing work on geoparquet 2, which will have more geo encodings and potentially a spatial index, so that one can determine the extents of the data, geospatial extents of the data in each row group and so on. Arrow is also a binary columnar format, but it's not optimized for on-disk storage. It's optimized for in-memory use, and it means that you can more or less memory map an arrow file into memory, and then or even into the GPU, because it's already in a format that the computer can work on. It has many of the same other advantages otherwise as Parquet, and GeoArrow is undergoing a very parallel standardization track, as GeoArrow is very parallel to GeoParquet in its standardization. Another interesting cloud native spatial format is flat GeoBuff, and this is a you can think about it maybe simplified as a binary relative to GeoJSON. So it's binary, but it's not columnar like Parquet and Arrow. It's row oriented, and so it's very easy to stream and even append to it if the file system supports that. And it has also a very interesting feature, which is it has an optional spatial index, and so it's possible to identify ranges of rows, for instance, that are within a certain region with the help of that index, and only load parts of the files with range requests. Another format that we here at Foursquare are really excited about is PM tiles. So when we're not working with the tabular data, or the tabular data is too big, we can, if we have vector data where every row describes a geometry, a very traditional technique is to tile that data into separate tiles, and then the client only loads the tiles that are suitable for its current viewport and zoom level. And traditionally, tiling would generate a huge tree. It could be thousands, or for an entire map of the world, base map down to block level, we could even talk close to 1 million tiles. And so we have an enormous amount of files to deal with in a complicated directory structure. And what you do in PM tiles is you basically have all of this in one giant file, but you have where you have an index that lets you know where the different tiles are located, and so you can load these with range requests as subchunks. And because it's a single file, and because it has a high level of internal compression, all the tiles are compressed internally instead of the external file being compressed. It's much smaller than the tabular data, and it's very easy to work with. You can just download and upload one single file and deal with an entire tile set in a single unit. Cloud optimized GeoTIFF, it's been around for a while, is obviously for raster data, and it's the same idea there. A single image, a very big image from a satellite, can have an internal tile structure, and so the client again can download only parts of the data from the cloud optimized GeoTIFF, and that enables these very big archives, even browsers, to work against very big archives, even petabyte scale archives of satellite data. So that's the formats, and obviously they're interesting in and of themselves, and many tools can work directly with these formats. As mentioned, there is also then the kind of complementary trend of development of open table formats. And so these today, the notable contenders here are Apache, say Iceberg, Hudi, and Delta Lake. And they all build on these cloud native formats, often Parquet as a primary component. And then you take a number of Parquet files, and then you, through this open format, add extra capability. We can now add schemas, table-like schemas, and so an entire collection of raw files can now be treated as a well-defined table with rows and columns. And not conventions, it's possible to use additional files to store those updates in a smart way. And then they also bring transactional safety. So not only multiple users can write and read from this table concurrently without seeing inconsistent data, but because this is not software, it's actually open formats. You can actually have multiple software, different types of software that implement these open table formats, accessing these tables concurrently. So you can have completely different systems accessing the same cloud data and still have transactional safety. And the advantages here that we're excited about is that these formats are open source and standardized. So not only are the open table formats standardized, open, but they're built on open cloud native formats, and much of the software that implements them, well, there is both commercial, but there's also open tooling. And so this is really a way to avoid vendor lock-in, and in many situations take control of a stack. And obviously cloud storage can be typically expected to be very cheap compared to a data warehouse, and it is indeed very reliable. So overall, it gives a promise that for some use cases, geospatial analysts and data engineers can take more control, simplify our data infrastructure, and we can easily stand up data stacks using open tools, and we can store our files in open formats and retain an interoperability with new tools and adopt quicker to new opportunities. So the third pillar is open data, and I've just picked the 3 initiatives that I think are very impressive. So we have the proto maps. So PM tiles the PM tile format is more or less developed to be able to provide as its main use case an open base map of the world. And there is active work on this base map, and it iterates every couple of weeks, and it's about 100 gigabyte a single PM tiles file that's available on cloud storage. And so if you have a PM tiles viewer, you can essentially just point it more or less to that URL. It kind of changes every now and then and so on, but and start consuming obviously a very high quality geospatial reference base map. Another effort that I recommend keeping a close eye on is the Overture Foundation. It's some of the biggest software companies in the world that come together to build open data sets, in many cases global, and they have administrative boundaries so far, transportation network, building footprint, and also points of interest. And when I last checked, it was about 200 gigabytes of open map data in Parquet format. And it's not a single Parquet file, but lots and lots and lots of Parquet files. So probably an open table format adapter there is is recommended. And then of course we've had for a number of years, we've had NASA satellite data, and that's Landsat and Sentinel satellites that have for decades been collecting imagery of the entire Earth and and it can be searched in temporal, and we can see how forest fires and various climate events and so on has changed the landscape. And so these are available in cloud optimized GeoTIFF format on, for instance, Amazon S3. So yeah, here we have some examples at the bottom of cloud optimized GeoTIFF data in Foursquare Studio, and up here we have a PM Tiles viewer that's showing the worldwide proto maps, base map. And tooling is very big, so I really have to make a few picks. But there's query engines. So what they allow us to do is to basically allow us to run SQL queries against cloud native data that's stored in cloud native file formats. And sometimes you can work directly against, as we will see in the demo, against files in cloud native file format, and sometimes you can connect against Apache Iceberg or other things. So ClickHouse and DuckDB are two open products, and there are commercial tools such as Databricks and Snowflake. I want to highlight DuckDB. It's an embeddable data. If you haven't looked at it, you probably have. It's an embeddable database with an incredible momentum. It allows us to query directly from cloud native formats. It can output results in cloud native formats. It has beautiful geospatial extensions. And I've even seen that there are extensions for open table formats like Apache Iceberg. It has cloud native support. You can query directly from the cloud. If you have your Pocket files on the cloud, just install the right extension. It's incredibly flexible in its deployment. You can just install it in a Python notebook to do ad hoc queries for a bunch of cloud native files you have or have found. It can be bundled as WASM into a browser, run as a web app. It can be run on a server in a traditional sense, and it's very lightweight, and it can even be placed in the infrastructure more or less next to your cloud native data to provide simple query access. So a very useful tool. Another tool that we find very useful is Tippecanoe. It can take something like a flat GeoBuff and tile it, a big tabular file with geometries, tile it into, and would store it directly as PM tiles, which is now very easy to move around and manipulate and open in other tools. So what are the opportunities for tool builders? Well, all of these formats really take big data capabilities to the next level. And so, obviously there's opportunities that we here at Foursquare are taking advantage of for that purpose. And private data, once you want to use these technologies, but you want to do it privately, and you need authentication, secure networking, private compute, and hosting them and sharing them securely with your customers and so on. It can be nice to have the help of a tool maker. And of course, we want to provide support both directly and indirectly for these formats. Either allow you to open and write these directly from our tools like Foursquare Studio, or integrate with the tools that work with them. I'm not going to go through the details, but we've done a significant amount of support. We work both in open source and in our commercial tool, and we're on a good way to have a good coverage. On the open source, we are active as leaders of Kepler-GL development. You may be familiar with DeckGL, and Loaders.gl is a framework where we have developed a huge amount of geospatial loaders, and obviously we keep developing support for these new formats as open source. It's a big community that involves a lot of companies. We're very proud of this collaboration, and it's part of Linux Foundation, OpenJS Foundation. Join us at openvisualization.org if you're interested in that angle. Now I'm going to hand over to Aditya, who's going to do a quick demo on how to use some of this tooling and technologies that we just looked at together with Foursquare Studio.
Hello, everybody. We'll get set up in just a second. I can share my screen. Sorry, 1 second. Here we go. Okay, so I'm gonna do a quick demo of all the stuff Ib is talking about. I am working on these types of things at Foursquare as an engineer. We're gonna use a Jupyter Notebook, which is a Python environment that you can run in the web. These things can be run in many other ways, but I just like this as a nice, quick ad hoc way of showing all the things we're working with. So I'm gonna take a big dump of Parquet files from our Places dataset, which you might be familiar with as Foursquare's data product, has a bunch of points of interest and some associated metadata about them. Here I have about 40 Parquet files ranging anywhere from 13 to 60 megabytes. Together they're like 4 to 5 gigabytes of data. It's a sizable data set. We're gonna use DuckDB to analyze this. So we can install it inside our Python environment. I already have it installed, so it's not gonna do anything there. We have a spatial extension that we can load that allows us to manipulate geometries, which is really helpful for obviously working with geospatial data. So we're gonna create a table from all of these files as a folder, and we're gonna take all the columns and we're gonna specifically take the longitude, latitude, and we're gonna treat it as a point. And this st point function comes from the spatial extension. So run it, it'll take a quick second. And once that's done, we will now have a table in memory that's pointing to those files. So we can describe that table and we see a bunch of different columns, things you might expect, an ID, a name, lat long, address, and some stuff Foursquare adds, like our estimation of the price and popularity and some of the visits data. We can run standard SQL queries on it. So DMA is, a market area, and we can, see that we have a number of them, 207 to be precise. So that's just an example of the query. We're running really quick queries over gigabytes of data, quite quickly. So for the purposes of this demo, I'm going to create a data set that is all the points that are east of the longitude -95, which is about Missouri. It's about St. Louis, and we're going to make sure some of the columns that we care about are not null. And we're gonna run this query really quick. So we see about 1 million rows, and it happened in a split second. And we can see a sample of those tables. The cool thing about the spatial extension is we can output out to various formats, and these are all powered by GDAL, which is like a common open geospatial tooling. It's written in C and has bindings and implementations for many of these popular formats. So there's an example of a GeoJSON, but today, because we're talking about flat geobuffs, we're going to output to flat geobuff. So it'll take a second, but it's pretty quick. And now we have a flat geobuff file, and we can see that it's about 251 megabytes. So that's a good size file. It's not huge, but it's a little too big to work with in our browser directly. Our browser memory might crash. So maybe we want to tile this data. So what we can do is we can use Tippecanoe, which is a tiling program that was developed by a really talented person, Erica Fisher, who was at Mapbox, and now she's at Felt, but it's open source. It's available for everybody to use. We can run it. This is actually a shell command that I can run within a notebook. We have some flags here to keep the tile size, no tile size limit, no feature limit for each tile. And then I'm making sure that the popularity is read as a float. I was running some tests where it might not have parsed correctly, but you can give type hints to Tippecanoe. So you can see it detects a flat geobuff, so it's using that index, and we can see it's gonna take about 90 seconds or so to tile this big data set. And so what it's doing is it's chunking up all these vector features, it's putting them into tiles, and it's creating a big PM tiles archive that will contain all of this tiled information, all this computation it's doing in one big file. So as you can see, it runs pretty quick. It's actually quite impressive how performant it is. And we can see that I generated GeoJSON a while ago, so we can see the flat geobuff's a little smaller than GeoJSON, but the PM tiles at 71 megabytes is about a third the size, and that's that internal compression it was talking about. So then let's say we want to visualize this. There's a number of ways to visualize it, but here at Foursquare we have our own visualization software that we're proud of, so we want to demo it. So we can use our data SDK, which we can install, which I've already installed, and I can import it. and I can upload the file. So it'll take a second to upload. Hopefully my internet's performing well today, but no, it seems to be going at a quick pace. So as it's uploading, it's just putting it to our cloud, it's creating some metadata, and it's, as Ib talked about, it's private by default, so it requires authentication to access. But once that's done, in just a second, we see it creates a data set, has this UUID. We can go over onto the Foursquare Studio tab, and we can see that, yep, eastplaces.pm tiles exists. We can go check it out. And this file is just sitting right on S3, and we're able to, with that index it was talking about, we can just see its metadata really quick that we can calculate, and we can say, let's create a map from this PM tiles data set. And boom, so now we have a map. It loads, we can zoom in, we can, see as we zoom in, the successive tiles load and these points fill in. Let's say maybe we don't love this color, we don't want a color based on popularity. Let's say we want a color based on price. And maybe let's check out the legend. There's 4 of them, and maybe this color scale isn't the most useful. So we'll say, let's go to something with 4 steps, and maybe we want to pick something that has sufficiently different colors for each category. So this looks pretty good to me. As we zoom in, we see a bunch of different points. Coffee is cheap, or this place is very expensive. So we see all that right in the map. We'll make the points a little smaller just for our purposes. So that's sort of the demo of how that works. We're going to add one final step here is we're going to publish this map, and this will allow us to both make it public, and it will allow us to embed this map inside the Jupyter Notebook that we are working in. So we can take this ID that we have right here. We can go back to our notebook, and we're going to use, we have another SDK called the Map SDK, which allows us to embed any map, whether it's a map from scratch or a map that's been published, you can work with it. And I'm using Sidecar, which is a really cool and a nifty little package that opens up this widget. And Jupyter has a thing called widgets, which allows us to work with interactive JavaScript objects in a Python environment. It has some like message passing between. It's actually really quite interesting. But so now we see we have the map right here. It's interactive fully. So I can say I want to zoom into New York, which I've put in the lat longs and the zoom here. So I run this cell and it zooms in on New York. And let's say I want to add a data filter. So I'm going to take that UID from the data set from earlier. I'll copy it into this cell. And I'll say I want only the field's popularity, but I want a range filter, which only the values from 0.9 to 1. I only want the most popular places. So I can run it, and we can see that the field has thinned out quite significantly, and we can see these are the most popular places. We can, of course, update that filter if we want. Let's say we want to look at the least popular places that we know of. And so I'll take that filter ID, we'll put it in there, we'll run it. And so these are the least popular places. And this map is fully interactive. We can get data out of it. We can put data into it. So we can get filters. We have the range filter. We can, get the layers that are available, which is in this case, it's only one layer. It's a vector tile layer with the associated metadata. So that's to recap. I'm going to close this map out. But to recap, we took this big parquet folder. We loaded it into DuckDB. We did some analysis on it. We took the data we wanted. We turned it into a flat GeoBuff from DuckDB. We were able to tile that with Tippecanoe, and then we were able to upload it to Foursquare Cloud to visualize and play around with the power of Foursquare Studio. And then at the end, we were able to embed that back into our Jupyter Notebook just for fun. But you can do the process in any order, so you can start with that embedding too. So that's the demo. Thanks for tuning in. And I'll hand it back to Ib.
Yes, so right, let me show my screen. And so yeah, we'd love to hear thoughts and questions and discussion. If we happy to be corrected if we got things wrong and challenged, or Any?
You know, type in questions into the text box. We can answer too.
I know, I feel so bad.
Are people able to talk, or are we restricted to typed questions? How does it work here? Okay. Is there anyone in the audience that's using any of these technologies today? So I think we can, so I'm seeing a couple of questions here. So would the demo be available to play around with? And Aditya, maybe you can answer. I assume we can make this notebook available in source format, for instance.
Yeah, I can definitely make the demo available. I can publish the notebook. I obviously the data I think we'll have to check with people if that's if we can share
Right.
that, but I can at least give some sort of sample of that.
So this was our commercial data, but we can find some data to.
The question on why we use DuckDB as opposed to PostgreSQL with PostGIS or other databases with geospatial extensions, any one of those is great. I'm a big fan of PostGIS. It's pretty good. The advantage of DuckDB is it ran straight in my process in the Jupyter Notebook. I didn't have to set up Postgres separately in the process and have the connection interconnection between them. DuckDB just runs straight in my notebook. It also, as it mentioned, we just wanted to give a demo of like a cool technology. It can compile down to WebAssembly, so it can run in the browser as well. So this is like a new sort of on-the-fly database, like lightweight database that people are excited about. Of course, most of these things will work just fine with PostGIS. These features of writing out to specific geospatial formats, that all works. So these tools are all very interoperable as long as you're using like standard formats. Yeah.
I think the thing that we really also, I was excited about was the ability to just basically specify the table by pointing at the cloud storage, right? So DuckDB has this ability to just point to a couple of, GeoParquet files on cloud storage, and with this HTTPFS extension, and then you can start doing ad hoc queries without any ingestion and so on. And so, but we have to look at each database, but other databases may require an ingestion step of the data and so on. So this ease of combining tools with open data without taking a lot of steps and not having to move the data or copy the data and so on is, I think, a very appealing aspect of this family of technologies.
There's another question. Any thoughts on applications, real-time applications with real-time data? There can be quite a few problems with cost and perhaps performance when large amount of data are changed in real time. Abe, do you want to take that?
Yeah, so I think, real time would need special techniques. And so as you write, real time data that comes in at a high speed, and typically you need to kind of append additional data, and then there are systems like Kafka on which you then kind of search through those archives. And I'm not super updated on what's happening with real-time data and geospatial in the geospatial domain. So I don't know if there's any cloud native formats covering that particular angle.
Yeah, to add on to that a little bit, I think one of the things that we mentioned as highlights of cloud native formats is their ability to be, you know, write once, read many times. The sort of constraints change a lot when you're writing a whole bunch of times. But you know, you want formats that are easily appendable. You want formats that that work well. I mean, flat GeoBuff, like it mentioned, is row based, so you can append more quickly. But at large scales, yeah, you're solving slightly different problems that we're optimizing for with these big sort of indexed files that we're looking at right now. Any more questions? I'll definitely try to have this notebook packaged up, and maybe we can share it out afterwards with some sample data.
Our goal is to follow up with a blog post, and we can make sure we have links to the notebook in that as well.
Okay, looks like that's it.
All right. Okay, well, thank you everyone for tuning in, and I hope you enjoyed.
Take care.